Welcome to this explainer. Look, take a nice, deep breath. I know math can sometimes feel, well, like a totally foreign language, right? But today, we're going to act like your own personal, private tutors. We're going to easily unmask these equations that look terrifying on the surface, but I promise you, they are actually quite friendly once you get to know them.
But before we look at a single formula, or do any math at all, really, let's answer the most important question. Why should you even care about this? Math isn't just some bunch of numbers trapped on a chalkboard. It is literally the hidden machinery running our everyday lives. This exact math, specifically the skill of reducing complex equations down into simple lines, is the invisible engine behind so much of the world around us. It's exactly how businesses calculate shopping discounts and run budgeting scenarios. It's how surveyors measure land and figure out complex travel logistics. It's used in building design to calculate labor costs. And yeah, it's even how telecom companies track and optimize your phone data usage. And today, we're actually going to solve a few of these exact real-world scenarios together.
So here is our roadmap for today. We're going to start by visualizing the logic, then move to level 1, the easy example. After that, level 2, building design, then level 3, the board exam challenge. And finally, we'll wrap up with a cheat sheet and a pretty awesome exam trick.
All right, let's jump right into section 1, visualizing the logic, equations in disguise.
Before we do any calculations whatsoever, let's visualize the actual geometry happening here. So, on the left, you've got this scary nonlinear equation, right? Something like 2 over x plus 3 over y equals 13. On a graph, that creates these messy, unpredictable, swooping curves. Variables hiding in the denominator tend to cause instant panic. But look at the right side. If we just imagine that the messy fraction 1 over x puts on a mask and calls itself p, and 1 over y puts on a mask and calls itself q, the equation magically transforms into 2p plus 3q equals 13. Visually, that messy curve just snapped into a friendly, flat, straight line. We aren't doing any hard math yet. We are literally just putting a simple disguise on a messy fraction so our brains can handle it without panicking. Makes sense, right?
Now, let's tackle section 2. Level 1, the easy example. This is just a warm-up using example 12.
Just like any good private tutor would tell you, whenever you face a word problem or a scary equation, always start by separating the noise from the goal. Map out exactly what is given and what is asked. Okay, so what's given here? We have two equations with fractions, 2 over x plus 3 over y equals 13, and 5 over x minus 4 over y equals negative 2. And what is asked? Simply find the values of x and y. See? Clear, calm, and structured. Now, the crucial point is how we execute this without getting overwhelmed. Step 1, we use our disguise. We simply substitute 1 over x with p and 1 over y with q. Boom, suddenly we have simple linear equations. Step 2, we solve those friendly equations using basic elimination, which gets us p equals 2 and q equals 3. But please listen closely to me right here, because this is where a bright orange trap is waiting for you in step 3. This is absolutely the most common mistake students make in exams. They solve for p and q, they feel super proud, and then they just stop. You cannot stop there. You must reverse substitute. Since 1 over x equals p and p is 2, well then 1 over x equals 2. Flip it around and x equals 1/2. Do the exact same thing for y to get 1/3. You always have to take the mask off at the end.
Moving right along to section 3, level 2, building design. Let's look at real-world applications with example 13.
All right, here's a very practical scenario straight out of the source material. Kavitha wants to construct 2 more rooms in her house. She's talking to contractors and trying to calculate exactly how many days it will take different combinations of men and women to finish the work based on their estimates. Once again, we don't panic, we just build our grid. What is given? Well, we know that 6 men and 8 women working together can finish the work in 14 days. We also know a second scenario. 8 men and 12 women together can finish it in just 10 days. And what is asked? Kavitha wants to isolate the time it would take if just 1 man or just 1 woman worked completely alone.
We're going to follow the exact same logic here. Step 1, we represent 1 man's work per day as a fraction, 1 over x. Step 2, we form our equation based on the groups. Since 6 men and 8 women take 14 days, their combined daily work is 6 over x plus 8 over y equals 1 over 14. Starting to look familiar? Yeah, it's our messy fraction from level 1. Step 3,
We substitute u for 1 over x and v for 1 over y to make it friendly. Then we solve for u, getting 1 over 140. Finally, step 4, we avoid that trap from earlier, reverse substitute. If 1 over x equals 1 over 140, then x equals 140, which means it would take one man exactly 140 days to build those rooms alone.
Okay, deep breath. Section 4, Level 3, the Board Exam Challenge. This one is all about measuring land travel.
I want you to stay totally relaxed because you are completely ready for this. In example 14, we're tracking a traveler who covers 370 kilometers total. He travels partly by train and partly by car, and his total travel time shifts depending on exactly how he splits the journey between the two vehicles. This is a classic real-world logistics problem.
Let's build our grid using the fundamental rule of travel. Time equals distance divided by speed. What is given? Well, scenario 1, 250 kilometers by train plus 120 kilometers by car takes exactly 4 hours. Scenario 2, 130 kilometers by train plus 240 kilometers by car takes 4 hours and 18 minutes. And what is asked? We need to find the independent speed of the train and the independent speed of the car.
Step 1. Let's write out the time equation. 250 over x plus 120 over y equals 4. Step 2. We use our trusty disguise. Substitute 1 over x for a and 1 over y for b. Step 3. Now we have 250a plus 120b equals 4. Yes, okay, the numbers are bigger and they might look intimidating, but I promise the logic doesn't change one bit. We solve this using the elimination method to find a equals 1 over 100 and b equals 1 over 80. And finally, step 4, our favorite part, reverse substitute. Flip those fractions around to reveal that the train travels at 100 kilometers per hour and the car travels at 80 kilometers per hour. See, you just flawlessly solved a really tough board-level math problem.
Finally, Section 5, Cheat Sheet and Exam Trick, how to solve faster and safer.
Here is your trick visualized as a simple flow. I want you to always approach these problems in 3 distinct phases. Phase 1, substitute the variables. Just hide the scary fractions so your brain stays calm. Phase 2, solve the simple linear equation. And Phase 3, honestly, I want you to mentally draw a giant red circle around this. Reverse substitute. This is your ultimate mark saver. Seriously, if you make it a habit to literally write reverse substitute at the very bottom of your test page before you even start doing the math, you will never lose those final crucial points.
And here is your 5-point cheat sheet directly from the chapter summary to lock in everything we've talked about today. 1. Linear equations can intersect, coincide, or be parallel. 2. Intersecting lines mean a unique, consistent solution, just like the exact train and car speeds we just found. 3. Parallel lines mean there's simply no solution at all. 4. You can confidently use the substitution or elimination methods to solve them. And 5. The absolute star of today, nonlinear equations with fractions can always be cleverly reduced to simple linear ones by using our mask. At the end of the day, math really isn't about blindly memorizing scary formulas. It's about seeing the simple logical patterns hiding right beneath the surface. Now that you know how to take the mask off and see through the disguise, what complex problem will you unmask next? Thank you so much for joining me on this explainer. Stay curious, and I'll catch you in the next one.